Hi guys, welcome to another lecture in the series General Inorganic Chemistry, and today we're going to be talking about chemical formulae and equations as well as stoichiometry, and this is part 1. So when we talk about stoichiometry, what we're talking about is the area of study that examines the quantities of substances consumed and produced in chemical reactions. And I'm sure you may have heard this word before. It provides an essential set of tools widely used in chemistry, including such diverse applications as measuring ozone concentrations in the atmosphere and assessing different processes for converting coal into gaseous fuels. And even in the texture and flavor industry, they are dependent on chemical reactions that occur when yeast ferment sugars to produce carbon dioxide and ethanol, right? So that is in making beer. So we have an equation here that has the conversion of starch using enzymes to glucose, which is C6H12O6, and then enzymes converting glucose into ethanol and carbon dioxide. So literally, stoichiometry examines the quantities of substances consumed and produced in the chemical reaction. So when you look at an equation, you think or should think what is consumed and what is produced. In this case, ethanol and carbon dioxide is produced, and in the second step, glucose is consumed, right? So when you think of a reaction, these are the words that you ought to be using. So that naturally leads us to chemical equations, right? So we represent chemical reactions by chemical equations, naturally. And so when the gas hydrogen, which is H2, represented as H2, burns, for example, it reacts with oxygen O2 in the air to form water. We write the chemical equation for this reaction as 2 molecules of H2, which is hydrogen, reacting with oxygen, which is O2. That gives us 2 molecules of water, right? And so when we talk about a balanced equation, we're counting the number. So 2 times 2 gives us 4 hydrogen, and this is 2 oxygen here. So on the reactants side, right, we have 4 hydrogen and 2 oxygen. On the product side, we need to have the same number of hydrogens and oxygens. So let's check. So 2 times 2 gives us 4 hydrogens, and this 2, which is our coefficient, says that we have 2 oxygen here. So does it balance? Looks like it, right? So 4 hydrogen, 2 oxygen, 2 oxygen. So our coefficients are 2, 1. So we generally don't write 1. We just understand that once there's nothing that precedes it, that it's 1, right? So that's 2, 1, and 2 are our coefficients. But as I said, we don't write the 1. All right, so our first question says we have 2 molecules of glucose here, and that gives us ethanol and carbon dioxide. And the question says, for the above reaction, A, identify the reactants, the products, and the coefficients. And part B says, is the equation balanced, right? So take a second and try to attempt this before you move on to the next slide. All right, so which one should we answer first? All right, let's go with A, reactants, products, and coefficients. So this is our reactant. These are our products, ethanol and carbon dioxide, and our coefficients are the numbers that precedes the molecules, right? And so 2, as we said, we don't write the 1 and 2, right? So 2 and 2 are our coefficients. And part B says, is the equation balanced? So how do we check this, right? We check this by counting our numbers. So for the carbon here, this carbon here, right, we can write, that is 2 times 6, and that is equal to 12 carbons, right? So we want to check the other side to see if we have 12 carbons, right? So let's check on the product side. So on the product side, we have 1, 2, and 2, 4. We have 4 carbons. So we can easily answer this question that the equation is definitely not balanced, right? Just by checking for carbon alone. So we have 12 carbons over here, and we have 2, 3, 4 carbons on the product side. And therefore, we can answer that question that the equation is not balanced. And a point to note here is that the smallest possible whole number coefficients need to be adhered to as well, right? And so we're not going to have like 10 molecules of a reactant and 20, like those. It's always the smallest possible whole number coefficient. All right, so even if you see a big number, you must try to reduce it to the smallest possible whole number coefficient. And just to mention that I had the same thing that I have up here, right? So for carbon, we have 2 times 6 is equal to 12 carbons, and on this side, on the product side, we have 2 plus 2, which is equal to 4, right? So it's saying the same thing that I have up here. All right, so we have another question which says the following diagram represents a chemical reaction in which the red spheres are oxygen atoms and the blue spheres are nitrogen atoms. So every red sphere that we see is an oxygen, and every blue sphere that we see is a nitrogen. So part A says write the chemical formulas for the reactants and products. That's part A. And part B says write a balanced equation for the reaction. And then part C says, is the diagram consistent with the law of conservation of mass? So before we get to the first two or the last two questions, let's look at the first one. Write the chemical formulas for the reactants and products, right? So here we can look. So take a minute or take a second to pause the video and answer the questions before you move on to the answer, right? So let's look at it. Here we have 2 oxygen atoms, which makes up a molecule, right? And here we have 1 nitrogen and 1 oxygen, which makes up a molecule. On this side, we have 1 nitrogen, right? And 2 oxygen here, right? Isn't that it? The blue represents nitrogen and the red represents oxygen. So we have nitrogen, oxygen, oxygen making up 1 molecule, right? So clearly we have a different molecule over here that is produced that is different from what is consumed. Remember those words? All right, so the answer is that the left box, which represents the reactants, contains 2 kinds of molecules. So if you had 2 oxygen atoms, those composed of 2 oxygen atoms, which is O2, and those composed of a nitrogen atom and 1 oxygen atom. So let's go back to it. So we have oxygen, oxygen, nitrogen, oxygen, right? So that is why we have O2 and NO. The right box, which is the product side, contains only 1 kind of molecule. Let's look at it again, right? Only 1 kind of molecule. is there. We have two kinds over here, one kind over here. So the molecule that is on the product side consists of one nitrogen atom and two oxygen atoms. So that's clearly NO2. So part B says, write a balanced equation for the reaction. So we have O2 plus NO2, plus NO gives us NO2, right? That's what we would write down. The next thing is we'll try to balance that equation. So just imagine for a moment that we don't have any coefficients, right? We would have one nitrogen here and we would have two oxygens here. And we'd have three oxygens on the reactant side and two on the product side, right? And then one nitrogen. So the nitrogen would have been fine because we only have one on each side, but we have to solve the issue of the oxygen, right? So trying to, and then sometimes guys with your balancing equation, sometimes it's just trial and error, right? In order to get a balanced equation. But we must remember that it has to be the smallest possible whole number coefficients. All right, so in order to balance out the oxygens, we could put 2 here and 2 here, and that will give us 4 oxygens on the reactant side and 4 oxygens on the product side, right? So that would, and then of course the nitrogens would also be 2, so that will balance our equation. And then our final question says, is the diagram consistent with the law of conservation of mass? And just in case you may not have been introduced to that law, it says the total mass of materials present after a chemical reaction is the same as the total mass present before the reaction. So what you want to do here is to literally count the atoms on this side and count them on the other side, that is the reactants and the products, and if they are equal, then the law of conservation of mass would have been adhered to. So what do we have here? So if you took the time to actually count it, you would see that there are equal numbers of nitrogen and oxygen atoms in the two boxes, that is on the reactant side and the product side. And so the drawing is indeed consistent with the law of conservation of mass. All right, so another important thing that we need to remember when writing our equations is that we must indicate the states of our reactants and products. And by this we mean if we have a gas, we need to write a G in brackets. If we have a liquid, we need to write an L in brackets. If we have a solid, we need to write it as a common S in bracket. And if we have an aqueous solution, we need to have AQ in bracket, right? So here, just for an example, so I didn't actually quite mention that aqueous means water, right? So just in case you forgot, if you have AQ, that means that we have water, aqueous solution of water, right? So here we have methane gas, we have oxygen gas, we have carbon dioxide gas, and we have water that is in the gaseous state. So sometimes simple symbols that represents the conditions under which the reaction proceeds appear above or below the reaction R. That is this arrow here. So sometimes, you know, you might see a delta, that is Greek uppercase delta, and this indicates that there is heat required, right? So in addition to our reactants and products, sometimes you have other conditions required for the reaction, and so you would see that either above or below the reaction arrow. Another thing might be temperature. You might see the temperature. I mean, apart from just heat, it might be a specific temperature. All right, so the other thing that we're going to talk about is formula and molecular weight. So the formula weight of a substance is the sum of the atomic weights of the atoms in the chemical formula of the substance. And so using atomic weights, we find, for example, that the formula weight of sulfuric acid, which is H2SO4, is 98.1 atomic mass units. So anytime you see AMU, we're talking about atomic mass units. And so if we go ahead and calculate the formula weight of sulfuric acid, we'll see here, well, clearly here we have 2 hydrogens, 1 sulfur, and 4 oxygens, right? So we can go ahead and plug that in here. So 2 hydrogens would be 2 multiplied by the atomic weight of hydrogen, which is 1, added to the atomic weight of sulfur, added to 4 times the atomic weight of oxygen, which is 16 atomic mass units. So once we do our multiplication here or multiplication here and we add them up, we get the formula weight of sulfuric acid. And so if the chemical formula is that of a molecule, the formula weight is also called the molecular weight, right? So it can be the same thing. So formula weight or molecular weight is the same thing if the chemical formula is that of a molecule. All right, so the question here is calculate the formula weight of sucrose, which is C12, H22, and O11. Take a second and calculate the formula weight of sucrose, which is table sugar. All right, so if you calculated 12 times 12 to be 144, and then 22 times 1, and then 11 times 16, and add them all up, you'd have gotten 342.0. all right, so clearly we're considering our significant figures here, or decimal place. All right, so the other thing that we want to calculate is the percentage composition from chemical formulas. Now, the percentage by mass contributed by each element in the substance, right? And so calculating the percentage composition of any element in a substance, sometimes called the elemental composition of a substance, is straightforward if the chemical formula is known. And so the calculation depends on the formula weight of the substance as well as the atomic weight of the element of interest and the number of atoms of that element in the chemical formula. So words are nice and well. However, you might understand better an actual equation, right? Or formula. So percentage composition of the element is equal to the number of atoms of element, right, multiplied by the atomic weight of the element, and that is divided by the formula weight of the entire substance times 100. So that is how we calculate our percentage composition. And of course, we want to see if we understand this formula. So calculate the percentage of carbon, hydrogen, and oxygen by mass in C12H22O11. All right, so using the same formula, right, we have 12 times 12, and let's go back to the formula again. The number of atoms of an element times the atomic weight of the element divided by the formula weight of a substance times 100, right? So atomic weight multiplied by the number of atoms divided by the formula weight times 100, and we get our percentage composition, right, of carbon, of hydrogen, and we do the same for all of them. So 42.1, 6.4, and 51.5. I hope you took the time to attempt that calculation. All right, so I'm sure you must have heard of Avogadros number and the mole, right? So it is considered by some to be challenging, but we're going to try to break it down. So for example, a teaspoon of water, which has about 5 mils, right? So if you put, I have a teaspoon and you have that full, that's equal to about 5 mils. That's also equal to 2.2 times 10 to the 23 water molecules. So can you imagine that number? That amount of molecules are held in that teaspoon. So a number so large it almost defies comprehension. We literally cannot comprehend 10 to the 23. And so chemists therefore have devised a counting unit for describing large numbers of atoms or molecules. So I know this side is a bit wordy, but let's try to get through it. In everyday life, we use such familiar counting units such as a dozen. We know that a dozen is 12. 12 of anything is a dozen. Less commonly we use gross, but that represents 144 objects, right? So in chemistry, the counting unit for numbers of atoms, ions, or molecules in a laboratory sized sample is a mole, and it's abbreviated MOL, which we saw previously, right? So we need to know that we abbreviate mole as common MOL. And we need to also know that in chemistry, the counting unit for numbers of atoms. So before we go any further, you need to be clear about what is an atom, what is an ion, and what is a molecule, right? Because how we count them in a laboratory size sample is the mole, and it's abbreviated common MOL. So 1 mole is the amount of matter that contains as many objects, so whether it be atoms, molecules, or whatever other objects that we are considering, as the number of atoms in exactly 12 grams of isotopically pure carbon 12, right? So you need to remember that carbon 12, right, is, we have other isotopes of carbon, but we're talking about carbon 12 specifically. So it's a sample that contains only one isotope of carbon, which is the carbon 12. So 12 grams of pure carbon 12, that is what a mole is. So let me repeat that. So 1 mole is the amount of matter that contains as many objects, whether it be atoms, molecules, or whatever other objects we are considering, as a number of atoms in exactly 12 grams of isotopically pure carbon 12. So from experiments, scientists have determined this number to be, or Avogadros number, right, which is 6.02 times 10 to the 23. So in honor of the Italian scientist Avogadro, it is often cited with the units of reciprocal moles, which we see here. The unit read as either inverse mole or per mole. It reminds us that there are 6.02 times 10 to the 23 objects per mole, right? So in other words, guys, we're saying that 1 mole of matter contains exactly 12 grams of isotopically pure carbon 12, and we're also saying that the amount, or the from experiments, scientists have determined that this number is 6.02 times 10 to the 23, which is our Avogadros number. So a mole of atoms, a mole of just like with the dozen, guys, dozen is 12, so it doesn't matter what we're measuring. Eggs, stone, what else can you think of? Tomato. It doesn't matter what we're measuring. A dozen is a dozen, right? So in the same way, a mole is a mole. So a mole of atoms, a mole of molecules, a mole of anything else all contain Avogadros number of objects. And so we have here 1 mole of carbon 12 atoms, they is equal to 6.02 times 10 to the 23 carbon 12 atoms, right? And 1 mole of water molecules is equal to 6.02 times 10 to the 23 water molecules, and 1 mole of nitrate ions is equal to 6.02 times 10 to the 23 nitrate ions, right? So notice here that 1 mole is equal to 6.02 times 10 to the 23 of either atoms, molecules, or ions, right? So spreading 6.02 times 10 to the 23 marvels over Earth's surface would produce a layer about 3 miles thick. I don't know if you can imagine that. I can't. Avogadros number of pennies placed side by side in a straight line would encircle the Earth 300 trillion times. That doesn't help either. I can't imagine that. But the point here is that it's a very big number. And it's a big number because these are all very small, right? And that leads us to a question which says, without using a calculator, arrange these samples in order of increasing numbers of carbon atoms. So the first one is 12 grams of carbon 12, 1 mole of ethane, and 9 times 10 to the 23 molecules of carbon dioxide, right? And so go ahead, take a second and see if you can place them in order of increasing number of carbon. So here, carbon dioxide, carbon, and carbon 12. All right, so if you had it in this order, then that would have been correct, right? So here we have the lowest number, and let me just read the question again. We're arranging it in order of increasing number of carbon atoms. So we're going from smallest to highest, right? So here for our carbon 12 grams of carbon 12 would be equal to 6.02 times 10 to the 23, right? And we already have in the question that we have 9 times 10 to the 23 molecules of carbon dioxide. So that is 1 carbon. This is not 12 carbons. This is saying that it's carbon 12, that isotope, right? And here we have 1 mole of ethane, but here, even though it's 1 mole, we have 2 carbons, right? So it would be 2 times 6 here, which would be 12 times 10 to the 23, right? I hope that is clear. So the smallest here would be 12 grams of carbon 12, and that's 6 times 10 to the 23, and then that's followed by 9 times 10 to the 23, and that's followed by 12 times 10 to the 23. So we have another question which says, calculate the number of hydrogen atoms in 0.350 mole of glucose. So take a second and try to answer this question. All right, so how do we answer the question, right? So we have moles and we want atoms. That's what the question asks, all right? We have moles and we want atoms. So in order to go to atoms, we have to start with moles, and then we have to go to molecules and then to atoms, right? So the question gives us 0.350 mole of glucose, and we have to multiply that by our conversion factor, which is our Avogadros number, right? So we have to make that multiplication, and whatever value we get when we do that multiplication is equal to number of molecules. And then our second conversion is from molecules to atoms, and we have our conversion factor here, which says 1 molecule of glucose is equal to 12 hydrogen atoms, and that should make sense to you, right? Because this is a molecule of glucose and it has 12 hydrogens, right? So this is now converting whatever value you'd have gotten after the first portion here would have converted our moles to molecules, and then here we want to calculate molecules to hydrogen atoms, right? So another way in which we can do the same calculation is to use statements, right? So we're going to look at the same calculation, but we're going to use statements. So here our first statement is 1 mole of glucose is equal to 6.02 times 10 to 23 glucose molecules, right? And 0.350 moles of glucose is equal to X molecules. So let me just go ahead and write that in. All right, so I hope, well, GLU, we're using GLU for glucose, right? So here we do our cross multiplication where we follow the black lines. So we multiply whatever it's at the end of the lines, right? So we multiply here by here and here by here, right? And then we make X the subject of the formula, and we get 2.10 times 10 to 23 molecules of glucose. So that is the first calculation. Then we want to calculate our molecule to atoms, right? So we have to write our second conversion factor, which is 1 molecule of glucose is equal to 12 hydrogen atoms. And since we already calculated up top here the molecules of glucose, we just plug it in here, and then we put our X because that is our unknown. That is what we're trying to find out. How much hydrogen atoms is in this amount of molecules, right? And that works out to be 2.53 times 10 to the 24 hydrogen atoms. All right, so moving on to molar mass. So the mass in grams of 1 mole, often abbreviated as 1 mole of a substance, that is the mass in grams per mole, is called the molar mass of the substance. The molar mass in grams per mole of any molecule is numerically equal to its formula weight in atomic mass units, and we should be familiar with every word in this sentence here. So for sodium chloride, for example, the formula weight is 58 0.5 atomic mass units, and the molar mass is the same thing. The only, well, it's the same value, but the unit is gram per mole, right? So the unit for molar mass is gram per mole. All right, so each of these samples contain 6.02 times 10 to the 23 formula units. So here we have 1 mole of oxygen gas that's in that balloon, right? And that is equal to 32 grams. We have 1 mole of water here, and it has a mass of 18 grams. And we have 1 mole of sodium chloride here, and it's equal to 58.45 grams, right? So because each of these solid, liquid, and gas, different states, right? And notice here that we have gas, liquid, and solid as our states here in brackets. They all contain the same amount of Avogadros number, right? Because they each represent 1 mole. All right, so now we're gonna start with our interconverting masses and moles, right? So let's look at this question. Calculate the number of moles of glucose in 5.38 grams times of glucose, right? So here we have to use our molar mass, and that is the conversion factor that we're using here. So 1 mole of glucose is equal to 180 grams, right? So that is our conversion factor that we're using here. And remember, our given unit and our desired unit. So here we have a conversion factor. We're given grams and we want to calculate moles. So that is how we do it, right? So the other question says calculate the mass in grams of 0.433 moles of calcium nitrate. So in this case, what's the difference? Tell me the difference before I move on. Well, if you said to yourself or said to me that in this case we have mole and we're trying to go to mass, right? So here we have our conversion factor, and notice that what the numerator is now grams and the denominator is now moles, because we're trying to get from moles to grams. And of course, this is our molar mass, right? So we need molar mass to convert moles to grams or grams to moles, right? And so we need to know our conversion factors here. In other words, we need to know our molar mass. All right, so I like to use statements. So we're going to answer the same 2 questions using statements. So here with the first calculation to go from grams to moles, we start off with our conversion factor, which is our molar mass, right? What we're trying to find is moles, that is why X is here, and we are given the mass. And so all we have to do is to cross multiply and make X the subject of the formula, and we get moles, right? So notice here that whenever we're doing these calculations, we have already looked at significant figures. And so whenever we are doing any calculations, we are to be cognizant of the rules of significant figures, right? So here we have 4 significant figures. Why? Because we have 1, 2, 3, 4 significant figures here. And we have 1, 2, 3, 4 significant figures here as well, right? So we have 4 significant figures. All right, so that is our conversion from mass, that is grams to mole using our molar mass. And then here, right, we're going from mass in grams. Sorry, we're going from mole to mass in grams. So as usual, we write our conversion factor out. 1 mole of calcium nitrate is equal to 164.1 grams. And we have the number of moles this time. And so our unknown is the mass, right? So once we cross multiply and we make x the subject of the formula, right, we get x, which is grams, and we use 3 significant figure as we see here, right? So I have done the same calculation, or gone through the same calculation using the formula that we were given previously, as well as using statements. So whichever way you find more comfortable, or just pick one way and just work with that and try to practice it over and over again until it becomes second nature. All right, so that is it, and that's all for now. Thanks so much for watching, and see you next time.